Bismillahirrahmanirrahim. Hello and welcome to Rahman Digital Production. This is lecture number 78 of physics. In today's lecture, we are going to discuss longitudinal waves. Yesterday, we discussed the uh, transverse waves, and according to that definition, those type of waves in which the medium particles are propagating perpendicular to the motion of waves. And yesterday we discussed that in greater detail. Today it is the turn of longitudinal waves, the same definition with only one exception. Uh, the type of mechanical waves in which the medium particles are propagating parallel to the propagation of waves is called longitudinal waves. Another definition is the waves that travel in a direction parallel to the direction of vibration are called longitudinal waves. Dear learners, I told you that there is one exception between the two definitions. So that is the parallel and perpendicular. In longitudinal waves, we defined it like the type of waves in which the medium particle propagate parallel. This parallel is a different word from that of transverse waves, in which we are saying perpendicular. So, ladies and gentlemen, there are waves which are producing by the slinky spring, and that slinky spring is shown in the figure as we used it in yesterday's lecture. Today we are going to discuss it again. Please pay attention. One thing I must mention here, that in case of transverse waves we were observing the crest and troughs. Here we are observing compressions and rarefaction. Rarefaction is also known as expansion. So that is, in the figure we are seeing the same slinky. Yesterday we discussed that slinky spring is lying on the table top, and one end is fixed with a wall or with a fixed rigid support. So when you are, yesterday we were moving the slinky spring to the right and left. Today we will push and pull it. As you can see that the direction of the push and pull is shown here. This double arrow sided symbol is showing that we are moving one time the hand in forward direction and second time in the left direction. So keep in mind, when you are pressing the slinky in the forward direction, so you will observe this portion, and as it is mentioned here that this is called compressions. What is compression? The area of longitudinal waves in which the density of medium particle is high is called compression, while rarefaction is the area of longitudinal waves in which the density of the medium particle is low. So, ladies and gentlemen, when you are pushing, you will see that the spring compresses and the density is increasing. This as a result pushes this area, and this area becomes a rarefaction then, and this area will become compression. So remember these things. And when this is compression and this is rarefaction, this compression will further press this one, the next area, which is rarefaction in this case. And when this area is compressing this by itself, it will again become as a rarefaction, and this will be compression. So they will push again the neighboring this one, and this will become compression, and as a result this area will become rarefaction. So in this way the wave is moving forward. In this way the wave inside the longitudinal waves is moving forward, in which this is the direction shown here. So one very important observation is that we are only witnessing the compressions and rarefactions, which is moving in forward direction. The rarefaction is the expansion. You cannot say here crest and trough. They are only produced in transverse waves. So by means of a slinky spring, we can show how longitudinal waves can be generated. The same slinky spring is stretched out on the smooth floor with one end fixed. Hold the other end of the slinky and move it forwards and backwards, that is push and pull, to compress and expand the slinky. Now dear learners, compressions and rarefactions, that is expansions are seen moving along the slinky towards the wall. The arrows, the double arrows, represent the motion of the wave along the slinky, which is in this case we are observing. First part, which is this one, is showing that neither you have pushed the slinky nor you have pulled the slinky. In this case, in 2 number, you are pushing. This double headed arrow is showing the movement of the wave. When you are pushing, you can observe here there is no compression and no rarefaction, but in this particular area you can see that when you are pushing the slinky in forward direction, then you are observing a very dense area of that spring, and that area is called compression. Now this compression will move forward, as you can see in the third case, and as a result the place where first we were observing the compression now became the rarefaction, and the neighboring spring area is compressed. So it means that this compression is moved a bit forward. Now in the third portion, the fourth one, which is this one, you can see that the compression is moved further. And similarly, when this is, you can see that these are the 1, 2, 3 rarefaction of the spring, but here 1, 2, 3, 4 in the fourth picture, and it means that it can go forward. So this compression is moving. Similarly, you can see that this rarefaction is also produced. The spring itself is not moving in forward and backward direction. It is on its place, but it is pushing the neighboring loops of the spring. And in this way, when you are again in that was the 5 one, in which larger rarefaction because the compression has moved forward. And in this case, again when we are pressing, the second compression is produced, and this compression is in moving forward direction. So here we can see in the middle, now this rarefaction, yeah, you can say that this expansion is also moving in forward direction. So ladies and gentlemen, this is the whole story. Compression and rarefaction are seen moving along the slinky towards the wall. The double arrow represents the motion of the wave along the slinky, while arrows, single-headed arrows to the left and right, represents that you are dragging it here, you are pushing it here. So you can see that the movement of the compression and rarefaction are produced, and those two single headed arrows are showing the direction of vibration, which is in the same direction is the displacement of the particles in the slinky. One thing, dear learners, you have to understand that these arrows are along the same line. That is to say, for longitudinal waves, the displacement of the particle is in line with or parallel to the direction of travel of wave motion, and that is what was the definition. If the compression or rarefaction is moving in this direction, the medium particle will also vibrate in this direction. So they are parallel. Just like in case of wave is moving in this direction in case of the transverse waves, but the medium particle is moving up and down, so it means it is at 90 degree, and generally we can see that the medium particles are vibrating perpendicular to the motion of the wave. So that is the main difference between. There are two main differences we can observe. The first one is that the medium particle in case of transverse waves is vibrating perpendicular to the motion of wave, while in case of longitudinal wave, the medium particles are vibrating parallel to the motion of the wave. That was the first difference. The second difference is that there are crest and trough. Crest and trough are there in case of transverse waves, while in case of longitudinal waves, we are observing compression and rarefaction. And rarefaction, we are observing these two. Okay, that's it for this topic. Now we are turning towards a very important topic, and that is the uh, properties of wave motion. If you want to understand and describe waves in a meaningful way, then you have to understand the properties, different properties of waves. There are different terminologies which can describe a wave. So let us understand those property with the help of this figure you can see on your screen right now. First of all, the figure shows a graph of the displacement of a rope along its length at a certain instant of time. The arrows on the graph show the direction of motion of the particles in the rope. A shorter arrow means a slower speed. A shorter arrow means slower speed. You can see that the arrow here is a shorter one as compared to the arrow here. So these arrows are showing that one particle is moving slowly and the other particle is moving with higher speed. So longer arrow means a longer speed. The dots, that is the particles without any arrows, mean that they are momentarily at rest. There is no arrow here, there is no arrow here, as well as at the very bottom position there is no arrow. So it means that they are momentarily at rest. Remember these words. Now let us turn our focus to crest and trough, because we are particularly dealing with the transverse waves, the rope waves. So we are writing crest and trough. So let us define. These are the high points and low points that characterize transverse waves only. What is for longitudinal waves? For longitudinal waves, the terms compression and rarefactions are used. So the highest point, which is this one, and the lowest point, which is this one, is called what? They are called the trough and crest. The lowest point is called trough and the highest point is called crest. So you have to understand this concept as well. Now the second one is the amplitude. That is the maximum displacement from the rest or central position in either direction. Now this is the central position you can see, and there is the distance on the lower side, and this is the distance on the upper side of the central position. That is the undisturbed rope. When the rope is not disturbed, neither you have dragged it in left direction on the tabletop nor to the right of the tabletop. So that is called the mean position. So whatever distance you are moving, that rope to the left or the right is called displacement. That is called amplitude. Now, what is phase? Very important term, and that is phase. When two particles are at the same position, in the same direction, having the same displacement, is called that those two particles are in phase. For example, this x and this x dash, they are in phase because they are moving both in downward direction. You can see that from the arrows. And similarly, y and y dash are in phase because both of them are moving in the upward direction at the same position, moving in the same direction. They are called 2 points such as x and x dash, and y dash are said to be in phase because they are moving in the same direction with the same speed and having the same displacement from the rest position. Any two crest or trough are in phase because this and this, or this and this, are in phase. Now the next one is the very important, and that is lambda, wavelength. And wavelength is denoted by a Greek word lambda. I am writing name for it, but that B is silent, lambda. People are calling it lambda. It is written as lambda, but B is silent, so we are calling it lambda, and that is always in all parts of the world is used for lambda. Wavelength. What is the wavelength? The wavelength is the distance between two consecutive crest or consecutive troughs. Consecutive crest or consecutive troughs. So this is denoted by this area. This is called, because in this place and this is one trough and this is another trough. Similarly, this is the one crest and this is the second crest, and it is denoted by the lambda. Remember that the unit for lambda is meter. The SI unit for lambda or wavelength is meter. Now next is very important, and that is frequency. The number of vibrations per second is called frequency. Or very technically, this is the number of complete waves produced per second. Let me tell you that if you are moving a rope in this direction like this, and you are observing it as this particular place, and in your hand there is a stopwatch, so you are observing that how many waves are passing through this particular point in 1 second. If two waves are passing in 1 second, then it means that the frequency of that uh, wave is uh, 2 hertz. Remember that the SI unit for frequency is hertz. Now, how you will understand that there is one complete wave? So it is starting from here, and when it is reaching again to its position, the dash portion is showing you that there is only one wave produced. But if there is a second wave, then this is called two waves. And remember that from where the wave is starting and it is completing one turn to be exactly at the same position, then we are saying this is the time period. The time taken for one wave to be produced is called time period. So if you are moving the rope to the left and right slowly, as in that case of the slinky spring, then it means that you are producing low frequency waves. But if you are moving your hand with faster rate, then it means that you are producing waves with high speed, and the rate will be more. Now we are coming to the time period. The time taken by a wave to complete one cycle. For example, if a wave is starting from here and is going and again coming to that position, for example, from here and then here, then it means that it is one, the time is noted by the stopwatch, and we can say that one wave is produced in 1 second, so the time period is 1. And the period is, because it is time, so you will say that its units is second. That means that if two waves are completing or produced in 1 second, then the time period of these waves traveling somewhere is 2 seconds. Okay, next is the wave speed. The wave speed is just like we learned that distance covered in unit time is called displacement. Remember that we are denoting this frequency by V, and this is the wavelength and this is the time period. Remember, this is a very famous equation relating frequency, time period and wavelength. If two of the quantities are given, you can find the third one very easily with this equation. So speed is equal to distance per time. So this is the speed, this is the distance, and this is the time. So we can say, very important, that T is equal to 1 over F. Now time period can be defined as the reciprocal of frequency. The reciprocal of frequency is called time period, and the reciprocal of time period is called frequency. These are the two equations we will discuss in tomorrow's lecture in the examples. But first we are defining this wavefront. If there are circular waves that are producing in water, so the waves is producing like this. So these all waves are producing like this. So the trough and the crest, this one, yani this whole area which is in circular form is called wavefront. Might be it is crest, might be it is trough, and that line is an imaginary one. So a wavefront is an imaginary line on a wave that joins all points which have the same phase of vibration. For example, a wavefront can be drawn by joining all the crest of a wave. The direction of wave travel is always perpendicular. This is the direction of wave front. So it will always be perpendicular to the wave motion. So you can see and observe that the same position I am making these lines. So these are, you can observe in the same. So this is an imaginary line which is connecting all the crust, all the troughs, and this is an imaginary line that is connecting all the crust, and this is also the crust. So these lines are called wavefront, and wavefront is a term which is commonly used in circular waves. So we discuss a very important mathematical formula. In a time of one period, a crest will have moved a distance of one wavelength. Therefore, the speed of the wave v is given by this formula. But you know that t is equal to, or f is equal to 1 over t. So we can write another very famous formula. V is equal to f lambda. V is equal to f lambda. This is very, very important formula, and you will use this for the rest of your life in physics. If you are going in higher classes, you saw it for the first time, but when you are completing education, which can never be completed, that is such a vast ocean, that is a sea. So till the last day of your life in physics, I am telling you, if you are choosing physics as your subject for master and PhD or MS, then you will see this formula. There is a work example, but we will do that tomorrow on these formulas. So that's it for today. Thank you very much for your time. Allah Hafiz.